All right, today we're going to break down a really powerful machine learning technique, one that's built for high-stakes problem solving. It's called Bayesian optimization, and it's all about one thing, making super smart decisions when every single try costs you a ton.
So, let's kick things off with a huge problem, one that even the biggest tech companies and science labs wrestle with. Think about it like this. You're looking for a needle in a haystack, right? But every time you reach in to check a new spot, it costs you a fortune. So the question is, how do you find that needle with the fewest tries possible?
And believe me, this isn't just some abstract idea. I mean, look at AI models. The amount of computer power you need to train them has just skyrocketed. Every time you want to tweak a setting to try and make it better, you're looking at a massive cost, both in time and money. You literally can only afford a few shots at getting it perfect. So this whole situation sets the stage for something the experts call expensive black box optimization. Now, I know that sounds super technical, but the idea behind it is actually pretty simple.
Okay, let's say you're tuning a neural network. You've tried a 5-layer model, a 10-layer one, a 20-layer one. Your best result so far is 81% accuracy with 10 layers. But here's the catch. You've only got the budget for, say, 1 or 2 more attempts. So what do? Try 15 layers? Maybe 8? Guess wrong, and you've just wasted a huge amount of time and money.
And that is the heart of expensive black box optimization. You're trying to find the absolute perfect setting for some system, but you can't see inside it. You have no idea how it works, and every single time you test a setting, it's a huge deal. It's kind of like trying to find the highest peak in a huge mountain range, but the whole thing is covered in a thick fog, and every single step you take is exhausting. So the process is dead simple, really. You just feed an input into this mystery box and it spits out a result. That's it. That's all you get. And you just have to do that over and over and over, basically just hoping you get lucky and stumble onto the best answer.
And look, this problem is way bigger than just AI. You know, there's this thing called Abrams' law. Yeah, that's Moore's law backwards. And it shows that in drug discovery, the cost of finding a new effective drug has been going up exponentially. This is a massive challenge in materials science, in mining, really any field where just trying stuff out randomly is way too expensive.
Okay, so if you've only got a few shots, why can't we just use the search methods we already have? Well, it turns out they're just not very good for this kind of problem.
Let's look at 2 really common ways people try to do this. On the left, you've got random search. You're basically just throwing darts, and you can easily waste all your expensive attempts looking in totally useless places. Then on the right, there's grid search. It's way more organized, sure, but it's also super rigid. And what if the real best answer, that perfect peak, is sitting right in between the points on your grid? Yep, you'll miss it entirely.
Clearly, we need a smarter way to do this. And this is exactly where Bayesian optimization comes in. It's a total game changer because it doesn't just guess, it actually learns as it goes.
So how does it work? Well, it's got 2 key parts. First, you have the brain. This is a predictive model, usually something called a Gaussian process, and its job is to build a map of the problem as it sees more data. And second, you have the strategy. This is a decision-making part, an acquisition function, that looks at the brain's map and figures out the absolute smartest place to look next.
So that brain is the Gaussian process. And its secret weapon, the thing that makes it so powerful, is that it doesn't just give you a single best guess, that solid line. It also tells you how uncertain it is about its guess. That's the shaded area you see. Where that shaded band is really wide, the model is basically saying, hey, I'm not so sure about this spot. But where it's narrow, it's confident. And knowing what it doesn't know is what makes the whole thing so incredibly smart.
So these 2 pieces, the brain and the strategy, they work together in this really elegant loop. The model makes a prediction, the strategy looks at that prediction and its uncertainty to pick the next place to test. We run that test, get a new piece of data, and feed it right back to the model. And with every single cycle, the model gets smarter and smarter.
Okay, this sounds cool in theory, but let's actually see it in action. We're going to watch, step by step, as it tries to find the highest point of some mystery function. All right, so we start with just one single random data point. Right now, our model on top, the Gaussian process, knows next to nothing. So you can see that shaded area of uncertainty is massive everywhere. And because of that, the strategy down below is basically shouting, I have no clue what's going on, let's just explore anywhere. Okay, now fast forward a few tries. It's starting to find a pretty promising spot over there on the left. You can see it's focusing its tests in that area, and because it's getting more data there, the model's uncertainty is getting smaller and smaller. It's exploiting what it thinks is a good area. But this is where it gets really, really cool.
Instead of just getting stuck on that one little hill, as soon as it feels confident about that area, the strategy totally pivots. Just look at that green curve now. It's basically thinking, okay, that hill's not bad, but hey, what about all this other territory over here that we know nothing about? It could be way better. Let's go explore. It's making that crucial switch from exploiting to exploring.
And boom, after it goes exploring, it finds the real highest peak way over on the right. From now on, the strategy is going to focus all its attention right there to nail down the exact maximum. So by smartly balancing that trade-off, exploring the unknown versus exploiting what it already knew, it found the absolute best answer without wasting a single extra test on those less promising areas.
Okay, so why does all this matter? Because this isn't just a cool theory. This smart search is delivering huge, real-world results, like right now.
I mean, it's being used by top tech companies to tune their most complex AI models. Nobel Prize winners are using it to guide the search for new, super-efficient enzymes. And it's even designing better molecules for stuff we use every day, like the OLED screen on your phone. The bottom line is the same in every case. It's speeding up discovery and finding better answers with way fewer experiments.
It's like Quan Nguyen says in the piece we're looking at. If you're still trying to solve these really hard problems with old-school methods like random or grid search, there is a lot of headroom to do better. You're basically just leaving performance on the table.
So when you boil it all down, Bayesian optimization turns what used to be a frustrating, expensive guessing game into a really strategic, intelligent search. It gives you a smart, principled way to handle that classic trade-off. Do I explore new territory, or do I exploit what I already know works?
And that really leaves us with one final question. Think about your own work, your own field. Where is your most expensive guessing game? And what incredible things could you discover if you started searching smarter, not just harder?